Over the years, the search for the perfect sound in the living rooms of Britain has caused endless boasts about who has the best woofers, tweeters, and crossovers. Well, today, a new product appears in the shops. This is it, to herald a new era of hi-fi snobbery. It's called the compact disc, which the manufacturers claim will mean the death of the gramophone record.
When you listen to a compact disc, it's immediately obvious that the quality of sound produced is far superior to that of earlier recording media. Now, it might be thought that this is entirely due to the use of advanced technology, particularly the use of a laser to scan the disc. But there's far more to it than that. And the secret lies within the compact disc itself.
Each CD has a spiral track, just like a gramophone record. But that's where the similarity ends. To start with, the track is scanned outwards from the centre, rather than inwards. It's also scanned at a constant speed, just over a metre a second, so that the disc slows down as it plays from 8 revolutions per second to less than 4. And finally, and perhaps most importantly, the sound is recorded on the disc in a digital format. Any sound, whether music or speech, can be represented as a waveform like this, an analog signal. With stereo, there are 2 such waveforms for the left and right channels. To convert each analog signal into digital form, it's sampled at regular intervals, and the value is measured. The value is represented as a binary number, a string of 16 bits. The bits are processed 8 at a time. Each group is called an information symbol, and the symbols are encoded before they're recorded onto the compact disc. This combination of laser scanning and digital recording was developed in the Netherlands by Philips in the early 1980s.
Here in the Philips Research Labs, this large-scale model of a compact disc is meant just as a showpiece, but it will serve to demonstrate some of the key features of the system. This light is reflected off the undersurface of the disc as it rotates. And as you can see here, sometimes it's bright and sometimes it's dark. But it is in fact in the timing of the transition from light to dark and from dark back to light that we find the coded information.
Along the spiral track, there's a succession of pits, depressions in the surface of the disc. By contrast, the parts of the track level with the surface are called lands. The pits are of different lengths, but they're all of the same depth, just less than a quarter of a wavelength of the laser light. So the light reflected back from the bottom of a pit travels about half a wavelength further, and so it's nearly 180 degrees out of phase with the light from the surface. Destructive interference thus makes the pits look darker than the lands. Each land to pit, or pit to land transition, corresponds to a 1 bit, with 0 bits in between at regular intervals. To make these recordings, the first stage involves a master disc. This is created using a high-power argon laser. The beam is carefully focused onto the blank disc and modulated with the digital signal. Once the master disc is completed, the process of creating submasters and final production discs is then purely mechanical. There's a lot of technology involved in reading a disc too. The laser spot on the surface of the disc has a diameter of about 1 micron. This has to follow the spiral track accurately, even if the turntable is slightly off-center. Ston Bakken from the Philips Research Labs shows us how this could be done.
To show that this is possible, look at this experiment. This uses a servo system with 3 spots, 1 central spot that reads the information, and 2 satellite spots on either side of the track. If you move the disk such that the central spot goes off track due to an eccentricity, for instance, one of the satellite spots sees less of the track, while the other one sees more of the track. This imbalance in reflected light then causes the servo system to correct the position of the central spot that reads the information. Now you can clearly see that the central spot moves with respect to the position of the track.
In this demonstration, the servo system controls a mirror which deflects the spot from side to side, so that it can follow horizontal variations in the track position. But there's also vertical motion to worry about, up to 1 millimeter. This also needs to be followed.
With the help of this experiment, we can show to you how the optimal distance between the lens and the disc is maintained. It's the focus servo. The light is first focused onto the disc, and on its return path it goes through the prism and then is focused onto 2 small spots on these detectors. By the positions of those 2 spots, we can detect the optimal distance between the lens and the disc in the following manner. If the distance between the lens and the disc changes, those 2 spots on the diodes move inward or outward depending on the distance between the lens and the disc. Then the servo system responds by moving the lens back to the optimal position with respect to the disc. As you can see, the lens is mounted onto a coil which moves in a permanent magnet, just like a loudspeaker system. By making use of the error signals, as have been shown before in the experiment, we can optimally control the distance of the lens with respect to the disc.
So sophisticated control systems make sure the laser spot follows the track as closely as possible. But so far, there's nothing to suggest any improvement in the quality of the recorded signal. And this turns out to be essential for the success of the system.
The CD system would be infeasible without an efficient error correction system, since cheap mass replication of gigabits of information is impossible without creating any error. Already a new freshly pressed disk may contain hundreds of thousands of errors, and due to handling, this number of errors may increase even more. For instance, a disk full of fingerprints might sound like this if you had no error correction at all.
When Philips sought advice about the error correction built into the design of the compact disc, they found it very close to their headquarters in Eindhoven. Working here at the university is a world expert on coding theory, Professor Jack van Lint.
Let me tell you about the origin of coding theory back in the late 40s at Bell Laboratories in the United States. Richard Hamming became very irritated by the fact that his computer was able to detect if an error occurred and then switched off. And every morning when he came to the laboratories, he found that the computer had switched off. And he said, if the computer can detect an error, it should be able to correct an error. And thus he discovered what is known as the Hamming code.
So, with digital representation of sound, error correction can be used to improve quality. In the CD recording process, the signal is first converted into digital form. Then it's passed through an error correction encoder, and finally it's sent to a special modulation encoder, which balances the number of ones and zeros recorded on the disc. The reverse happens when the disc is played back. The signal passes first through a modulation decoder, then it goes to an error correction decoder, and finally it's converted back to analog form to be sent to the amplifiers and loudspeakers. But how does error correction work? we asked Professor van Lint to give us a simple example.
Well, we have seen that music is recorded digitally as a long string of zeros and ones. In reading the information, an error can occur. That is to say, a 1 is interpreted as a 0, or a 0 is interpreted as a 1. Now, let us look at an example. Here is a very short symphony, 1, 0, 1, 1. Now, here is a scheme where I will send 7 bits instead of 4. I have drawn 3 circles and numbered the parts into which the plane is divided, 1, 2, 3, 4, and the outer parts, 5, 6, and 7. I shall write these 4 bits into the parts numbered 1, 2, 3, and 4. Now the remaining 3 bits are determined by the following rule. In every circle, the number of ones should be even. So here at the bottom we have 2 1s and a 0, so the remaining bit is a 0. Here we have 3 1s, so the remaining bit must be a 1. And in this circle we have 2 1s and a 0, so the remaining bit must be a 0. And we have changed 1, 0, 1, 1 into 1, 0, 1, 1, 0, 1, 0. Now suppose an error occurs. Let us say an error occurs in position 3. I shall mark it by an arrow. So that means this 1 is read as a 0. Now the receiver sees that something is wrong in circle 1 because the number of 1s has become odd. Something is wrong in circle 2 because the number of 1s is again odd. However, in circle 3, the number of 1s is still even, so the error did not occur in that circle. The error has occurred in the intersection of circles 1 and 2, but not in circle 3, so it must be in this position. So we now know where the error is, and since there are only 2 symbols, we can change the erroneous symbol into the correct one. This is an example of a 1-error correcting code, and we have used only 7 symbols instead of 4.
The error-correcting codes employed on CDs use a special type of arithmetic called a finite field. For example, this is how addition works when you only use numbers from 0 to 12. You add the numbers as usual, but for your answer you take the remainder on dividing by 13. So 8 plus 11 normally gives 19, but if we take the remainder on dividing by 13, we get 6 as the answer instead. 10 plus 7 normally gives 17, but the remainder on dividing by 13 is 4. We do the same for multiplication. 7 times 2 is 14, but the remainder on dividing by 13 is 1. 6 times 8 is 48, but the remainder on dividing by 13 is 9. Now the important feature of a field is that you can divide by any non-zero number. If you look down the column for, say, 4, then every number from 0 to 12 appears just once. So 9 times 4 equals 10. That means 10 divided by 4 equals 9. And so on.
What I will explain is the concept of the Reed-Solomon code. This is the type of code that is used on the compact disc. However, for the sake of simplicity, I will not use long strings of zeros and ones, but assume that the music is recorded using elements of the field F13, that is to say the integers from 0 to 12. Let us assume the music is given as the string A0 to A10, and as before I will add some extra symbols. So the symbols C0 up to C10 are the original symbols, which I have indicated by the red color, and two more will be added on, which I have indicated by the blue color. And here is the rule. The sum of the symbols C0, C1 up to C12 should be 0. And if we take each symbol multiplied by the number of its location, and we add all these, the sum should again equal 0. These two equations determine the final two symbols. Now again, let us assume an error occurs, say in position with number I. So instead of CI, we receive RI equals CI plus E. E is the magnitude of the error. And the remaining symbols RJ are equal to CJ. Now if we do the calculations again, the sum of the received symbols will not be 0, but it will be equal to E. So we say, oops, an error has occurred. And in fact, we know the magnitude of the error is E. The second calculation, R1 plus 2R2, etc., yields I times E, since the error in position I was E. Now, since division is possible with these symbols, we can divide the second by the first, finding the number I. That is to say, we have the magnitude of the error and the location of the error, and we can thus correct. Here's an example. 11111 is a word in this code. Now here we have received an 8 in position 0, 1, 2, 3, 4. So the size of the error, E, equals 7, and the position of the error, I, is 4. When we do the calculations, we find R0 plus plus R12 is 7, so indeed E is 7, and R1 plus 2R2 plus etc. is 2. Now we divide 2 divided by 7, since we're working mod 13, is equal to 28 divided by 7, and that is 4. So we have found the position of the error. Now R4 was 8, so we know that C4 should be 8 minus 7, and that is 1. The error has been corrected.
The codes employed on CDs work in a similar way, but they involve binary numbers. For instance, here's how you add 3-bit numbers. In this example, 011 plus 001 equals 010. And here's how you multiply them. You can see that 110 times 010 gives the answer 100. And you can divide by any non-zero number. If you look along the column for, say, 101, then each of the 8 binary numbers appears just once. So 110 times 101 equals 111. That means that 111 divided by 101 equals 110, and so on. And it's just this idea, but with 8-bit numbers, that's used for compact disc codes. Codes that can even cope with slots cut in a disc.
Although the average disc will not be damaged as badly as this one, it still can be played by a good compact disc player. But this is how it would sound if there were no error correction involved. But thanks to error correction, it actually sounds like this.
To deal with these bursts of errors, the compact disc system uses two codes rather than one. The first encoder takes groups of 24 information symbols and produces groups of 28 intermediate symbols. These are then fed through delay lines of increasing lengths. Then the second encoder converts groups of 28 symbols into groups of 32 output symbols. This means that two successive information symbols are now at least 32 symbols apart when encoded. The information is interleaved in time. And it's these groups of 32 code symbols which are sent to the modulation encoder and then written to the disk. Now the decoding process is the reverse of the encoding. Each group is processed by a decoder to give a group of 28 intermediate symbols. This decoder can correct up to 2 symbol errors. The groups of intermediate symbols are then passed through delay lines of decreasing lengths. And another decoder processes them to give groups of 24 information symbols. This decoder can also correct up to 2 errors. And it's these groups of 24 information symbols which are turned into the analog output signal. So let's see what happens when there is a burst error. The burst error affects several adjacent code symbols, and the first decoder can't correct them all, but it will almost certainly detect them, and its output will contain the special symbols. But the delay lines spread these out. So now the second decoder only has to deal with one error in a group, and it can easily correct that.
And the result of applying all this theory to the recording of sound is a remarkably faithful reproduction of the original signal, even if your own copy of the disc is somewhat damaged.